Welcome back to section 2.1, the derivative and the tangent line problem. And so we are continuing on with example 4. And this one says find the derivative, that's what this is right here, for f of x of the square root of x, and find the slope of the graph at the given points, and discuss what's happening at 0, 0. So we're going to go first of all and find the derivative. And remember, the derivative of a function goes with the uses the formula f of x plus delta x minus f of x all over delta x, and that's the limit process. I forgot that, the limit as delta x goes to 0. And so we are going to go ahead and plug in what we know up here, and by doing that we're going to say the limit as delta x goes to 0 of the square root of x plus delta x minus f minus the square root of x all over delta x. And so with this one, this is one where we have to rationalize the numerator to get rid of it, because if I do a direct substitution at this point, you'll notice that the top becomes 0 and the bottom becomes 0. So I have to multiply by the conjugate, and the conjugate I'm going to use is the square root of x plus delta x plus the square root of x. So you'll notice the only thing that changed was the sign. And the reason we do the conjugate is so that we can use a difference of two squares when we're multiplying these together, and it makes our multiplication a little bit easier. It also simplifies the problem. So if I go ahead and multiply this out, I end up with the top, the square roots go away, so I get x plus delta x. The middle terms, when I FOIL, will drop out, so I don't need to worry about those, and I'm subtracting away x. On the bottom, I'm not even going to bother multiplying the conjugate by my delta x. It's just too much work, and it's really not necessary in this case. You'll see what happens as I do this, and typically that is the case. It's not necessary to multiply everything by delta x along the bottom. It'll just make things a little bit more a mess, and you're going to end up factoring it out anyway, so let's not do the work twice. So simplifying the top up here, the x's cancel out, and the delta x, there's a delta x top and bottom that would cancel out to be 1, so that leaves me with 1 on top, and the square root of x plus delta x plus the square root of x on the bottom. And now if I take delta x to 0, this guy becomes 0, and I'm left with the square root of x plus the square root of x, which gives me a final answer of 1 over 2 square roots of x. So that is my slope of my tangent line. That's the derivative, the other name for it. And so now if they ask me for what is the slope at 1.11, I don't need the y value, I just need the x value, because that's kind of what we're going with. So if I want the derivative at 1, I'm going to plug in 1 into this problem, and you can see that the slope becomes a half. If they ask me for the slope at 4.2, well, I'm going to plug 4 in for x into my slope equation, and when I simplify that, I get 1/4. And then they want to know what happens if discuss the end behavior of 0, 0. So I'm going to plug in 0 into this function just to see what happens. And when I do that, when I take the square root of 0, I get 0. 2 times 0 is 0, so I end up with 1 over 0. And when you end up with 1 over 0, that basically means that you are dealing with a vertical asymptote. So there is a vertical asymptote there, and where the graph is, and so at 0, 0. So that's basically our end behavior. Moving along to example 5, it says, go ahead and find the derivative with respect to t of this function. So what we do is we're going to go through, and remember, our derivative and the limit process are the same thing in this case when we do our delta x goes to 0. So now I'm just going to plug in this, and in my function, remember that my limit as delta x goes to 0 is f of x plus delta x minus f of x all over delta x. And basically the t there, I could do it in terms of t. It doesn't really matter. I always say t's are tipped over x's, so we're just going to do it as x just because it doesn't really matter what variable we use in this case. So I'm going to say my function is 2 over x plus delta x, and then my other function is just 2 over x. All of this divided by delta x. So this is kind of an ugly numerator, but basically what ends up happening here is we got to get a common denominator to add these together. So this guy over here, the x, is going to get multiplied by x plus delta x, top and bottom. And remember, the reason we do top and bottom is so that we're multiplying by 1 and not changing the problem any. And this guy over here gets multiplied top and bottom by x. So now we have a common denominator for our derivative, and we basically can say the top becomes 2x minus, and when I distribute this 2 to this guy, I get negative 2x minus 2 delta x. On the bottom, I'm not bothering to multiply this out. I'm going to take x times x plus delta x, and all of this thing is supposed to be divided by delta x. Well, remember when you're dividing fractions by fractions, remember delta x is delta x over 1, that I multiply by the reciprocal. So this thing really goes away, and actually will end up, doesn't really go away, but it ends up just moving up to the bottom right here, and I'm just going to put it on the end. So instead of dividing by delta x, we flip it over and multiply by the reciprocal, which gives us this problem right here. So now we can simplify. My 2x and my negative 2x will go away. So I'm left with negative 2 over delta x. Well, the delta x's will go away. And so when I do my limit of delta x goes to 0, I have negative 2 over x times x plus delta x. Well, remember that our delta x's are now going to go to 0, so we're going to do our step of calculus, which gets rid of that right there. So I really have x times x, and so my final answer after my limit is negative 2 over x squared. And remember, this is our slope machine. This, if I gave you a point, you could plug it in and find the slope at the given point in the function. And so then we end up with this example where we're dealing with absolute value. And when we're dealing with absolute value, it's a little bit different. It says it is continuous at 2. However, we have to use one-sided limits because of the nature of the absolute value of this function, because of the nature of absolute value. So when I go about this, I'm going to say, okay, well, let's first just think of what the graph would look like. If I just kind of quickly sketch a graph, it says it's at negative 2, so my graph is going to be 2 units over, and it's going to look like this. So I've got my absolute value. So it is continuous at 2, but there's a sharp point there. So what would happen is if I was to take the derivative of this function, which I can't do it because what happens with the slope of this line? Well, the slope of this line, that's really what we're asking you for, is negative 1. So the slope of the line, if I was graphing the slope, I would be at negative 1. If I was graphing the slope of this line, I'd be at positive 1, which would be 2 different values. And so because of the sharp point, we end up with it not being differentiable at that point. So that's what we're basically looking at. And so when we go ahead and do this, we're going to say, okay, we're going to take the limit as x goes to 2 from the negative side of this function. And so we can say, well, that's like f of x minus f of 2 all over x minus 2. Well, plugging in our absolute value into our f of x, we end up with the absolute value of x minus 2, and then when I plug 2 into this function, I get just minus 0 all over x minus 2. And so at this point, if I'm looking at it from the negative side is this guy right here, and so you can see, we talked about that just a second ago, the slope, which is really what we're looking for, is negative 1. So then, if I ask to find the limit as x goes to 2 from the positive side, well, we'll use the same setup. And this up here is just, this function, what I'm writing, is basically what we've been doing just without all the delta x's. And so in this case, again, we end up with the absolute value of x minus 2, that's supposed to be an absolute value, minus 0, all over x minus 2. Well, when I simplify this, again, we're looking at from the positive side, so we're looking at it as we approach over here, which means that we get a positive 1. So since this function is not differentiable at 2, and so the only place that we can't find the derivative of the function is at 2, 0. And so that's basically what we're trying to get at. So it's not differentiable. So whenever you have a sharp point in a function, you can't differentiate, because if I was to graph these, from this side, we'd be down, our graph of our derivative would be down here at negative 1, and the graph of our derivative after that would be positive 1, and so you can see they don't approach 2 points. And so then our final example deals with this function with x to the 1/3, and is it continuous at 0. So basically, we're going to go through and say f we're gonna say f of x equals our x to the 1/3, and when we do this, we're gonna follow our limit process again, and this time we're gonna do our limit as x approaches 0, and we're using the alternate form f of x minus f of 0 all over x minus 0. So plugging in what we know, we can say that our limit as x goes to 0 of this, we get x to the 1/3 minus 0 all over x. And so now, with a little bit of simplification, and when we take x goes to 0, well, we first would get this. We would first get 1 over, well, hold on, let me simplify this. So before I do my limit process, I'm going to say, oh, my limit as x goes to 0, this thing will simplify to 1 over x to the 2/3, which basically means now if I do my limit, this bottom part will become 0, which gives me 1 over 0, and right there, as soon as I see this, I know I have a vertical asymptote at 0, and so that's really what we're trying to find. So there's a vertical tangent line or a vertical asymptote, and sometimes we call this a vertical tangent line at that point. And so that's really what we're trying to look for in this case. And so that concludes our examples for 2.1. Thank you for listening.